Welcome, everybody, to our distinguished webinar series in Artificial Intelligence and Cybersecurity. Today's talk is When Serverless Meets Servers, featuring Dr. Boris Grot, professor of the School of Informatics at the University of Edinburgh. Dr. Boris Grot is a professor in the School of Informatics at the University of Edinburgh, where he leads the Edinburgh Architecture and Systems Lab. His research focuses on understanding and alleviating efficiency bottlenecks and capability shortcomings of processing platforms for data-intensive applications. Dr. Boris is a member of the Micro Hall of Fame and a recipient of multiple awards for his research. He was the program co-chair of Micro 2022 and the General Chair of HPCA 2024. Dr. Grot, it's a pleasure to have you. And with that, I'll let you share your screen and the floor is yours.
Awesome. Thank you very much for that introduction. It's a real pleasure to be here. Okay, let me first share, make sure that works. Okay, I think that's looking good, right?
Yep, great.
Awesome, fabulous. Cool. Thanks for having me. Yeah, it's a really fantastic opportunity to present some of the stuff we've been doing. And so, yeah, thanks for giving me the floor. Okay, so I understand that kind of people may have a bit of a diverse background, not necessarily in serverless. So I'm going to spend a few minutes just simply telling you about kind of serverless, what that is, where that's coming from, and why it's actually really cool and hot at the same time. So let me fire up a laser pointer while I'm at it. Okay. So, all right. So kind of thinking about the cloud, when people deploy applications in the cloud, right, historically, the way it would be done is, you have a meaningful kind of non-trivial application, let's say some sort of an online shop. And the way you would roll it out is you just rent a big fat virtual machine from a cloud provider like Amazon, right? Now, the picture I'm showing here, kind of this example, right? Let's suppose this online shop, it has some sort of a, user interface front end, right? So this is basically a web server. And then let's say there's a bunch of kind of backend logic, right? So there's a recommendation system, product catalog, kind of like a bunch of accounting functionalities, right? And then like maybe some, customer account profile sort of thing, right? And then all of that is backed by a database and a data access layer, okay? So again, so kind of traditionally, this would be rolled out in a virtual machine. And if you need to scale, right, if the traffic increases, kind of the shop is really popular, you'd simply roll out more of these virtual machines, right? And again, each VM is pretty fat. It takes a while to boot. And if only a part of the system is suddenly a bottleneck, right? So for example, you're using some sort of a fancy machine learning model for the recommendation system, right? There's no way to really just scale that part of the system. You're really scaling at this really, really clunky granularity of a big fat VM. Okay, so, some time back, people realized, okay, this is not really great, right? And so there was a trend toward microservices, which is basically a way of breaking up these complex monolithic applications and rolling them out as kind of independent logical units that are also deployed kind of separately. And that's kind of what this picture shows, right? So we have a bunch of these units, they can talk to each other, and each of these units would be deployed as a separate standalone virtual machine, right? And what's really nice now is that we can scale these units independently, right? So now if my recommendation system becomes a bottleneck, boom, I can simply deploy more VMs that are just running the recommendation system, okay? So this sparked a trend toward greater degrees of modularity and disintegration in cloud applications. And kind of this has culminated a few years back in a trend called serverless that basically takes this whole paradigm to the extreme, deploying data center applications as collections of really, really tiny stateless functions. Okay, so let's talk a little bit about serverless, right? So as I just said, it's basically a way to deploy applications as collections of stateless functions. Now, the individual functions are invoked on demand, right? So for example, a user clicks something, types something in, a function can call another function, right? That's kind of what the picture here shows, right? So, F2 would be spawned because the user did something, but then it can invoke F4 and maybe F8 in this here picture, okay? Now, functions themselves are stateless, but the applications are stateful, right? The stateless nature of function simply means that a function cannot hold mutable state beyond function call boundaries, right? So when a function completes, if it had any side effects, right, the next invocation of that particular function cannot see any modified state, right? Now, that basically means that any state modified by the function has to be externalized, right? So it has to be either communicated to another function or sent to some sort of, a storage layer, okay? That does involve inefficiencies. So for example, a function cannot just like freely talk to another function, right? The communication either happens at invocation boundaries or through a storage layer, right? That is very different to virtual machines that can just directly talk to each other through like sockets, things like that, okay? Now, the really cool thing about stateless functions, because you may be wondering, like, why are they stateless, is that it facilitates extreme scalability, okay? And that is the really, really amazing aspect of the serverless model, okay? So kind of scaling of these functions on demand and load balancing traffic across the functions is done completely by the cloud provider. So the developer truly does not need to worry about this. That is really cool because that is not so easy for virtual machines, okay? And the scaling bit of this is really facilitated by the stateless nature of the functions, right? So because the functions cannot hold any mutable state, the service provider can shut them down or spin them up on demand. And in fact, if you run software, in a virtual machine or as like a native process, we kind of intuitively understand that if the process is not running or if the virtual machine is down, right, that application is not available, right? If there are no instances of that virtual machine up. Serverless is different, right? I can have 0 instances of a particular serverless function or application, but the application would still be available. And if a request for that application came in, right, the service provider would simply spin up the necessary functions on demand, transfer requests to them once they're up and serve traffic, right? So like compared to virtual machines where you have to have at least one instance available in order to serve traffic, and moreover, you have to pay for the virtual machine if it's idle, right? So even if it's not doing anything, you have to pay for it. Serverless flips that whole model on its head, right? So developers pay only when the function is executing useful code, right? And they basically pay only for the CPU time that code is running and the memory that it's using, okay? It's a radical departure from the conventional virtual machine kind of based deployment model. And this is like really, really cool, right? Like developers really love this. Okay, now, like it's clear why developers appreciate this. Why do cloud providers want to do this? The reason why cloud providers really like to do this is they get much higher density and utilization at the server level. Now, you might think that when a user is paying for a virtual machine and that virtual machine is idle, that the cloud provider is happy. Actually, they're not happy. And the reason why they're not happy is because they have an idle resource. Even though they're getting paid for that resource, they can't monetize it more, okay? With serverless, developers have a financial incentive to reduce the memory footprint of their functions and reduce their runtime, right? So the execution granularity is extremely fine. And so that basically gives cloud providers these minuscule instances that they can really pack very densely into their servers, right? And so that basically allows them to dramatically increase server utilization, right? Like actual usage, like useful cycles on that server, and to co-locate an immense number of these serverless functions, basically, pushing utilization to the limit, which is really, really great from kind of resource efficiency, also energy efficiency perspective, right? Because idle resources burn power, and that's not actually good for anybody. Okay, so that was a little bit of a long, but hopefully useful and important overview of the serverless model. And the question is kind of like, what are the implications of it, right? Now, at a very, very, very high level, right? What is good about the serverless model is it's very simple for developers to program with it. Now, serverless is not a programming model, it's a deployment model, right? And from that perspective, there's really nothing special that they can do for serverless, right? In fact, if you have an application deployed or kind of developed as a set of microservices, porting it to serverless is pretty trivial. I can attest to that because in my group, we've done this for a bunch of existing microservice-based applications. Like porting is not difficult, right? We kind of routinely have interns doing ports of an entire application from microservices to serverless, right? Deployment is amazing. Like that's what developers love the most, right? That they just kind of like, boom, kind of upload their collection of containers that make up the serverless application to the provider, and then the provider just manages it. And then they kind of like the pay-per-use aspect of the serverless model. Now, what is not good about it is kind of poor performance and low efficiency in kind of various ways. So one of these is the frequent scaling of these instances due to traffic changes, right? So, traffic goes up, a bunch of instances get spinned up, and then it dies down, and the provider, of course, has an incentive to shut these instances down in order to, free up resources and run something else in their path, right? But that means that then again, when the traffic increases, right, these instances have to be brought up, and likely that happens in the critical path of, application kind of being used, right? And so then there may be delays associated with these instances being provisioned. As I said earlier, functions are stateless, so there is an enormous amount of communication through storage that introduces sometimes significant performance bottlenecks, right? And then there is a massive degree of function interleaving on a server, which leads to poor microarchitectural efficiency. Okay, now that's just a sampling of the issues, but I think these are some of the dominant ones. Okay, so that is bad, right? But that's kind of, in a way, that's good for researchers because then, hey, we can innovate in this space, right? But the problem then is that every cloud provider, Amazon, Microsoft Azure, Google, Alibaba, Huawei, right? They all have their proprietary serverless stack. They all offer serverless, to developers, and you can kind of run your functions in that model, right? But their stacks are proprietary, so you can use it, but you can't innovate there, right? And so that's the challenge. And so that's kind of what we started out with, kind of realizing that, oh, wow, it'd be really great to work in this area. This was several years ago at this point, right? But kind of there's no representative stack where we could confidently say, hey, this is really representative of what providers are using in the cloud today, okay? So, providers kind of really cutting edge stuff. Obviously, they have an incentive to innovate because it's a competitive market space, right? Research offerings at that time were kind of incomplete. And so we stepped in and we basically designed a complete sort of end-to-end serverless stack for serverless research, and it's open source, okay? And that's what I'll tell you about in the next couple of minutes. So obviously, serverless stacks are complicated, right? You have a schedule, a runtime, containerization, virtual machines. There's a bunch of stuff. I mean, there's no way we can possibly develop all of these components. So the idea from the get-go was, let's take the state-of-the-art open source sort of components, and then let's glue them together in a way that would essentially give us a representative system. And so that's what we did, right? So for the cluster scheduling and serverless function runtime management, we used Kubernetes and Knative. For containerization, we use Containerd. For micro VMs, we used Firecracker and gvisor. Now, let me tell you something about micro VMs. So this was one of the key ways, that was one of the key things that was missing from open source projects before we kind of did our thing. And so micro VMs are basically like virtual machines in the sense that they provide a full isolation for security purposes, right? Which is what everybody cares about in the cloud these days, of course, right? But they are much leaner than traditional virtual machines. So they boot much faster. They're much more agile compared to traditional virtual machines. So they're basically like super massively stripped down VMs. Okay. So Firecracker was a project from Amazon AWS. gvisor is Google's project, so we support both in our system, but most of the stuff I'll be talking about is based on Amazon Firecracker. And then for the communication fabric, we used Google's gRPC. So again, if any of you kind of work in this space, like sort of do stuff in the cloud, hopefully a bunch of these names will ring a bell. And so then we sort of packaged all of this up, lots of student and intern time, and we called the resulting system vHive. Okay, so at this point, it's been several years. We've put a lot of effort into it. At this point, vHive is really a complete ecosystem. It's not just a serverless stack. Okay, so the stack itself is pretty representative. We specifically modeled it on what we understand to be the AWS stack. And in fact, at the time, we had quite a bit of communication with folks at AWS, and we sort of got there, like, yeah, kind of what you guys are doing is sort of meaningful and, somewhat representative at least. We're not claiming that like the performance numbers you get with vHive running on, modern hardware would be exactly what you would get, with exactly the AWS system. But, it's kind of, I think, as good as we can do in an open source project fashion. Let's see. Yeah, it's been quite a bit of like really good adoption over the last few years. A bunch of universities use it for research and teaching. Actually, a bunch of companies have adopted this as well. That's been very gratifying to see. In addition to the serverless stack, we also have kind of one, but actually it's really two serverless benchmark suites. So we have a bunch of real world applications like ML training and inference, analytics workloads, packaged as serverless workflows, right? And then we have a bunch of standalone kind of simple serverless functions. I mean, things like, for example, rotate an image, like run a AES encryption task. So these really simple things packaged as standalone serverless functions. And these are really great for microarchitectural research. And like you can like, simulate them in a state-of-the-art full system microarchitectural simulator. So that's really, this stuff, you can use it for kind of large-scale systems research, and this stuff you can use for microarchitectural, like processor research, memory system research in the server space. Okay. So this is actually our website. You can go look this up. This is the screen you'd get. There's a bunch of kind of tutorial material, videos, stuff like that. So as you can see here, the vHive ecosystem has grown quite a bit. So I've talked about the vHive framework, and I mentioned the vSwarm benchmark suite, right? We have other components. So for example, a bit less than a year ago, we rolled out something called Stellar, which is basically a continuous benchmarking system running in several cloud providers. So here's a picture of that, right? So this is, for example, showing the tail latency of a very simple function running in 4 different cloud providers, right? So this is Amazon AWS, Google, Microsoft Azure, and Cloudflare, right? And this shows the tail latency for execution of this function when these instances are what we call warm, so deployed, right? So like here you can see that Amazon is consistently the slowest, right? And here at the bottom, we have Google Cloud Run being on average the fastest. Okay, anyways, so that was kind of a cool pitch. vHive, all of this stuff is open source. If you are, if you're into serverless, you want to play with serverless, you're very welcome to, to play with it. It's all on GitHub. There's also an online community. We also have occasional meetings of like users and maintainers of this stuff. I mean, it's a really big and active project at this point. And we would love to help you guys get started if you're interested. Okay, So I'm going to talk about, depending on how we go with the time here, I will tell you at least about one and hopefully two different things that we've done with vHive on the research side. Okay, so the first one is we're looking at the cold start problem, right? And the issue here, I very quickly alluded it a few minutes ago, is that cloud services exhibit bursty traffic, right? So traffic, kind of load increases, then it diminishes, right? Service providers, for serverless, they will spin up instances on demand, but then when the load subsides, they will shut them down. And then, of course, when the load increases again, kind of spinning up these instances of functions may basically result in poor performance because we're waiting for these functions to launch. We're waiting for these micro VMs to come up, for the code and data to be downloaded, and for the instances to be fully available. Now, the state-of-the-art solution for this problem is basically an approach called snapshots. And the idea is once an instance is fully booted, right? So the micro VM has loaded, the runtime has loaded, right? We've loaded the whatever data the instance needs to operate, right? At that point, we'll literally take a snapshot of the physical memory of the machine, right? I will capture the architectural state of that virtual machine, right? And we'll save it away. And then next time, instead of literally going through the full boot process, we will simply load the memory image and start from that snapshot, from that checkpoint, right? Okay, the question is, that sounds really good. How effective is it at solving the cold start problem? So first, let's spend a minute in order to understand how, how snapshots work. So a request comes in, right? And first, of course, it goes through the scheduler that, like companies like Amazon and Microsoft, they, of course, make insane investments to make sure that the scheduler is, predictable and low latency. It's not always that, right? But that's a topic for another time, right? But for now, let's just kind of assume that, the vast majority of the time, this is not where the problem lies. Right. Then, we need to load the function state from the snapshot. And here we're going to look at vHive with Firecracker micro VMs and snapshot support, right? All of this technology is basically kind of the Firecracker micro VM and snapshots. That is straight kind of open source stuff from AWS Lambda. Lambda is Amazon's serverless framework. Okay, so the way that this loading function state proceeds is in two steps. First, we restore the virtual machine monitor state. So first, we restore the architectural state. That is basically a bunch of architectural registers. This is really fast. And then the guest memory file, which is essentially the snapshot, gets memory mapped, but its content is not populated in physical memory. Okay, so the mappings are there, right? But the physical memory has not been loaded with the content. And then the virtual machine is resumed from the point at which the snapshot was created, which is basically when it can, start taking new requests. Now, once all of that has been done, right? So the VM is kind of officially up and running, the connections get restored between the function instance and various control plane components like the scheduler. And then we can start processing the function invocation. So now we're here. Okay, so now this chart shows the performance of baseline snapshots compared to kind of the golden scenario where we don't need to restore, okay? So when we execute, when the instance is up and running, completely like ready to process things, it's fully warmed up. We call that a warm start, okay? And those are the left bars, right? So for each pair of bars, that would be the bar on the left, that's the warm start. And then when we need to kind of load everything, right? In this case, we're loading from a snapshot. That is a cold start, right? And that's the right-hand bar for every workload here, right? And so what we can see from this graph, right? And then the y-axis is the latency, right? The execution time of everything. Loading the VMM, establishing connection, processing the function, right? And what we can see is that, loading from a snapshot. Now, again, this is snapshot. We're not booting anything from scratch. Is about 20 times slower than a warm execution, right? And what we see is that the cold start's delays are dominated by restoring the connection state, right? That's kind of the green portion of each bar here, the lower part of the visible bar, and then executing the function itself, right? Loading the VMM, that is super fast. That's definitely not in the critical path. That's the blue part. That's not even visible here, right? And I think what may seem really, really surprising is, gee, we're loading things from a snapshot, right? Okay, intuitively restoring a connection would take some time, but why is function processing, being so much slower than before, right? So let's understand what's going on there. So functions, even really simple ones, and remember, as I said earlier, developers have a real incentive to minimize the runtime of their functions, right? So they have a fairly sizable memory footprint, kind of measured in tens, maybe hundreds of megabytes, right? The footprint is often dominated not by the data, but by the code libraries, kind of various frameworks. There's a big kernel footprint, right? You have the network stack, things like that. Now, snapshots rely on lazy paging, but that basically means that when the snapshot is loaded, the guest memory file is mapped, but physical memory is not populated, right? And then what happens is when things start running, you get page faults that get served one by one sequentially, right? So we run, execute a load instruction, the load kind of experiences a TLB miss, we do a page table lookup, and then the page table says, this page is not in memory, gotta load it from disk, right? Or maybe over the network, right? And so then everything pauses because now you have to load, the page, execute, do a bunch of IO, and that's a very long wait time, right? And so it's this lazy paging behavior, right? These kind of like every time the page turns out to not be in memory, gotta load it from storage, right? That is the performance killer for functions that are being restored from snapshots, okay? So these kind of serial slow disk accesses, or could also be loading things over the network, that is really what kills the execution of functions once they're loaded from a snapshot. Okay, so here is a study we did, right? So what we did was we kind of ran a particular function back to back a bunch of times, and then we traced the page faults using user fault FD, which is a stock Linux user level page fault handling mechanism. Okay, and so what we did was we basically recorded the memory usage of a given function across a bunch of back-to-back invocations, right? And so what this graph here is showing is the y-axis shows the memory footprint in the number of small pages. Small pages are 4 kilobytes, right? And then the y-axis shows these stacked bars where the blue component shows the pages that are the same across all of the invocations, I mean, every single one. And then the red shows the pages that are unique, right? That do not appear in every single one invocation, right? And so what we can see here is that, the memory footprint for these really short running functions is not trivial, reaching up to maybe 100 megabytes for this set of applications. And the memory working sets are shockingly stable across invocations. And I should note that the inputs to the invocations are different every single time, right? So the commonality is, up to 99%. So it's about 75 to 99% common across these different invocations, right? And the reason for this incredibly high similarity is because, you don't, of course, reuse much of the data across invocations, but you reuse pretty much all of the code. And the instruction footprints, the code footprint for these functions is pretty darn humongous. So, okay. And so kind of this, this consistent behavior, right? The same exact page is being used time after time. That is, that gives rise to this idea of, hey, why don't we just record and then, record the set of pages that comprise a function's working set, and then we can just, the next time that function kind of executes and it's loaded, right? Let's just prefetch those pages, right? Let's proactively bring them from storage into the physical memory ahead of the function's execution, okay? And so that's what we did, right? We designed a system called record and prefetch, or REAP, right? REAP snapshots. So the idea is, again, this stuff, this conceptually, this is really, really straightforward. So the idea is, again, we intercept page faults when a function executes using the Linux user fault FD user level page fault handler, right? We record the full working set in a very small kind of separate file that is stored alongside the snapshot, right? And so then this file is, like I said, it's stored alongside the snapshot. Oops, sorry, it's supposed to be animated here. And then it can be stored, on disk of a particular node, or it can be stored in cloud storage like AWS S3, something like that. Okay, then when a particular function is invoked and it needs to be loaded from the snapshot, right? What happens is, so kind of the snapshot goes through the same steps as before, right? So the guest memory file is not brought into physical memory, but what we do then is we read this working set file from disk, and then we prefetch all of the pages that are specified in the working set file into the guest memory, right? So here we go, we load it from disk. We proactively load the pages into the guest memory. Now we do this in one shot, so we exploit, really good sort of disk behavior. We also service all of these page faults at once, right? So we don't have to keep taking interrupts in order to service one page fault at a time, right? And so then we install kind of, and then as the function starts running, it will, of course, encounter an occasional page that is not part of the snapshot, right? That would be the red pages, right? The red parts of this graph here, the unique pages, right? And so those would be installed on demand exactly as in the baseline snapshot-based system, right? So some of the working set we install proactively, and then some of it gets installed on demand. Okay, so the idea is to trade off a teeny little bit of extra storage in order to record this working set file, for a much faster fault start. Okay, so now we compare the kind of the baseline Firecracker-based snapshots. So that is the left-hand bar in this figure. In the previous figure, that was the right-hand bar, right? And then we compare that to our REAP system, right? And now that is on the right. And the y-axis shows the execution time, the latency. Of course, lower is better, right? And so what we can see is that, on average, REAP reduces complete end-to-end function invocation time by 3.7x. And where we specifically look at the upper portion of the stacked bar, which is the function processing time, that is reduced by 4.5x, right? So it turns out that REAP can slightly reduce the connection restoration file, because part of connection restoration is actually loading the code associated with that. And so that REAP can speed up, but of course the actual, communication with the control plane of the serverless system, that of course REAP cannot really help with. On average, we find that REAP eliminates 97% of all page faults in the studied applications, right? So that's kind of where the benefits come from under the covers. Okay, so kind of summarizing this part of the talk, as I said, baseline snapshots suffer from a high page fault overhead due to lazy paging. There's a lot of commonality, right? And so that we can exploit through this record and prefetch approach, right? And what's been really cool is, we did this project, we based it on Amazon's Firecracker snapshotting, Firecracker micro VM, but also their snapshotting system, right? And then we open sourced our work, and then Amazon team integrated REAP into their Firecracker system, right? So that has been very, very gratifying. Of course, they have like Amazon, pick this up and integrate it into their system. Okay, so I think we're doing well on time. Let's see here. And I understand that the questions will be at the end. So since we're doing well, I'm gonna, I have time to talk about the other kind of work that I wanted to highlight here. And I'll try to finish in maybe 10, 15 minutes so that we have time for questions. Okay, so this previous part of the talk, I focused on cold invocations. What happens when a function gets called, when it gets invoked, and there are no instances running, and so, or all of the instances are busy, and the provider has to spin up a brand new function, right? So that's a cold invocation. Now we're going to look at what happens when an instance is actually running, and surprisingly, there are bottlenecks associated with that as well, okay? And so that's what we'll talk about right now. Okay, so we're switching gears now, right? Before we were talking about kind of this distributed system, right? We have a scheduler and it decides, a request comes in and it says, gee, do I have any functions run? Do I have any instances of that function running? Do I need to spin up a new instance or not? Now we're gonna zoom in on a single server. Now this is a generic server in the cloud, right? And, there are a bunch of different functions that have all been scheduled onto that server. Okay, and so we're going to take a look at this one server and what are the kind of implications of the serverless model from that perspective. So first of all, function execution times tend to be pretty short, right? In many cases, and again, I'm certainly not claiming that all of them, but in many cases, based on real data from cloud providers who have kind of open sourced their data sets or published papers, kind of characterizing their serverless workloads, we know that many functions run for like literally a few milliseconds, okay? Compare this to a scheduling quantum in Linux, right? You have multiple processes running in Linux, and the scheduler will context switch among them, right? Typically speaking, for a normal priority process, the Linux scheduling quantum is something like 10 to 20 milliseconds, okay? So this is much shorter than a typical time slice in Linux. Functions have pretty small memory footprints. So for example, Amazon AWS, the smallest memory kind of instance that you can get for serverless functions is 128 megabytes, so very fine grained. And this may seem kind of surprising, but an individual function gets invoked relatively infrequently, maybe once every few seconds or minutes. That's pretty common, sometimes even less frequently. So that may seem surprising, right? Because, hey, if everything is so amazing about serverless, how come, and some applications are intuitively very popular, how come functions are invoked so infrequently? And that has to do with one thing that I have not yet talked about, and it is a little bit, orthogonal to this talk. It simply has to do with the economics of serverless, right? So cloud providers ultimately do not want all of the cloud to be serverless. They still want to sell you VMs, and VMs make a lot of sense for workloads that are continuously running. They're constantly processing a certain load. And so the economics of serverless is such that if you have a continuous load, you have a constant stream of requests, right? You're better off running this on a traditional VM where, you boot up as many VMs as you need, and you're processing the steady load on these VMs. If you were to process the steady load on serverless, where you would constantly, like nonstop, be processing requests, economically, it would cost you, several times more than running on a VM. It's not like 500 times more, it's not like it's 100% unaffordable, but it's considerably more, right? And of course, developers are not stupid. They understand sometimes, somewhat, to some extent. They kind of have a clue as to what they're doing. They're particularly sensitive to cost, right? And they understand sometimes when serverless makes sense economically and when it does not, right? So basically, the stuff that gets run in serverless is more things that are sporadic, or when you have a big load spike and you just simply, want to kind of offload some of the traffic from your VMs and just like, deal with the spike by throwing it over to some serverless instances until the spike subsides, right? That is basically when the serverless makes a lot of sense. Okay, so that was a long aside, just so that you understand why the serverless functions in practice are invoked relatively infrequently. Now, the implications of these three things, short function execution time, small memory footprint, and relatively infrequent invocations, are that, if you look at a modern cloud server with like dozens of cores and hundreds of gigabytes of physical memory, you can pack thousands, like literally thousands of functions on a single server, okay? there's a huge degree of interleaving between two invocations of the same function, right? So here, if this function gets invoked once, by the time it will be invoked again, like hundreds, if not thousands, of other functions will execute on the CPU between two invocations of the highlighted function here. Okay. So, what are the implications of this for the microarchitecture? Okay. I don't expect anybody in this talk to be, a CPU microarchitecture expert, right? So I'll try to keep this, fairly high level. But, please bear with me and, do ask questions if something is not clear. Okay, before we dive into the microarchitectural stuff here, here's a graph that kind of shows, what happens due to this interleaving at the application level. So what I'm showing here are two kind of simple tasks packaged as serverless functions. So one of them here is the authentication function written in Python, right? And another one is an AES encryption function written in another programming language called Node.js. Both of these are extremely popular for serverless development. What we can see here is the inter-arrival time of these applications running on a real server with other stuff, other functions also kind of running on that same server, right? And so the x-axis shows the inter-arrival time, and the y-axis shows the slowdown compared to like literally back-to-back execution. Like requests are constantly coming in, right? And there's no gap between two requests hitting the same function instance, right? And so what we can see is that as the inter-arrival time grows, the functions take longer and longer to complete. And once we get into the range that is the typical inter-arrival time for functions in the cloud, and when I say typical, this is based on the data published by cloud providers like Microsoft Azure, for example, right? What we can see is that the slowdown is actually quite substantial compared to, like back-to-back executions, right? So what is going on here? Well, longer inter-arrival times means that there's a higher degree of interleaving. So a bunch of other functions are running on the same CPU between two invocations of the same function. That increases the slowdown, right? The slowdown increases by like up to 2.7x. That would be the point over here. Over here, it's 1.5x or so, right? That is really, really substantial. And the question is, okay, high inter-arrival times, high degree of interleaving. Why is there such a high slowdown? Like, what is going on? So in order to understand what's going on, we basically did a bunch of experiments, right? And what we did was we ran these functions on modern cloud servers. So this is Intel Ice Lake server CPU. This is pretty recent. 32 cores, a very large last level cache, over 50 megabytes. We use 20 diverse serverless functions from our vSwarm serverless suite. 3 different runtimes. These are the most common runtimes for serverless: Python, Go, and Node.js, representing compiled, interpreted, and jetted runtimes, right? And then we have 2 execution scenarios. We have back-to-back. So this is like we're just banging, same function, running time after time, again, with no breaks. And then we have the interleaved execution where we run a function, and then there's a big gap, other stuff runs, and then that function is invoked again. And so now we get a little bit microarchitecturally. So let me kind of walk you through this graph here. So here on the x-axis, I'm highlighting 9 functions. Actually, it's 3 functions: AES, authentication, and Fibonacci, written in 3 different programming languages, right? So it's these 3 functions in Python, Node, Golang. And then the mean here is for all 20 functions in our suite. So it's these 9 plus the other 11. Okay. And then the 2 bars show the performance back-to-back execution, and then the interleaved execution. Now, the y-axis is CPI. CPI is cycles per instruction, so it's a low-level metric of performance, but intuitively, we want each instruction to execute is as few cycles as possible. So higher CPI means more cycles for every instruction. That intuitively means things are slower, right? And so what we see is that interleaving drastically increases the CPI, so the number of cycles per instruction, by up to 300%, right? And so basically, kind of the issue here is that in back-to-back executions, the microarchitecture is warm. So all of the different structures that modern CPUs use to achieve high performance, caches, branch predictor structures, different kind of prefetchers, right? They're all warm. They're all warmed up. They all hold the state necessary for that particular function. However, under interleaving, these structures get thrashed because other functions run, right? And so the caches get polluted, right? The data associated with a particular function gets kicked out of the caches. The branch predictor kind of structures hold completely different state. And so when that function starts running again, all of these microarchitectural structures need to be warmed up, right? That takes time, and that results in very poor performance. Okay. And so when we actually look at where exactly do the cycles go? Where exactly are we losing performance, right? We use this well-established methodology to understand where microarchitectural performance goes across 4 categories, right? So again, this is kind of thinking CPU executing instructions, every instruction takes some time. Where is that time going, right? So here at the bottom, we have retiring, right? And that is good. That means instructions are completing. We want things to just be completing, right? We don't want to wait for anything. So this is the good category. And we can see that that is a tiny, tiny portion of the time, right? So most of the time, we're not able to complete or retire instructions. Most of the time, we're waiting. So the other 3 categories are quote unquote bad, right? They're stalls. We're waiting for things to happen, right? So this category here, this is fetch, right? So that basically means we're waiting for instructions, right? So we're waiting for the instructions to be delivered. We're waiting for address translations associated with instructions, things like that. Then we have bad speculation. So that is basically branch mispredictions, right? Think back to your computer architecture class, processor design, right? We have a branch predictor, right? Because it is called when a function starts running, it will make mistakes. It will make a lot more mistakes than when it has been fully trained, right? And so, that is a category of performance loss. And then we have the backend. The backend is associated with actual instruction execution. We fetched it. It's a correct instruction. We did not mispredict the branch, right? So we start executing it, and then, we stall. And usually the stall means we're waiting in memory. That is the most common source of stalls, right? So again, often it's basically missing in the caches, right? But now it's waiting on data, not on instructions. So here we'd be waiting on instructions. Here we're waiting on data, right? And so what we can tell is that the front-end cycles, they're by far the biggest category of performance loss for these presumably warm executions, but they're not super warm, right? Because in reality, things are not being executed back to back. There's interleaving, right? And so we kind of call this thing, we call it lukewarm executions, right? Because the function is technically warm. We're not like restoring it from a snapshot or anything like that. It's sitting on the server, but it takes so long between 2 invocations of this function that the CPU itself loses all of the microarchitectural state, right? Now, I should say that we used Intel Ice Lake for this here graph. We also did the same experiments using an older generation Intel server, Broadwell, and the latest generation called Sapphire Rapids, right? And on all of these server CPUs, we basically see exactly the same trends. Okay, so then kind of trying to understand, gee, where does the performance go? Right? Like what is happening? Like why are we waiting for instructions for so long? What we find is that when we look at the last level cache, when we like this ginormous, last level cache, right? What we find is that the misses, and that's what the y-axis shows. It shows the number of misses per 1,000 instructions, MPKI means misses per kilo instruction, per 1,000 instructions. We see that there are very few for the data, right? But for instructions, oh, sorry, there are very few in back-to-back executions, I apologize. But in the interleaved executions, the misses per kilo instruction is very high, right? Kind of averaging about 30 or so. And the majority of these come from instructions, right? So about 18 instructions out of 1,000 have to wait for the instructions to be delivered from main memory, right? Because the L3 is the last level cache on the processor, right? And so every time we miss in the L3 means the data, instructions in this case, is not on chip at all. We have to go to main memory. Memory is incredibly slow. It takes like literally hundreds of cycles in order to get, information from memory. And so in this case, every single time we have an instruction miss, and we have to go all the way to main memory, the processor is stalled for hundreds of cycles, and this happens 18 times on average for every 1,000 instructions, right? And so it's these misses for instructions in these lukewarm executions that are basically the critical performance bottleneck in this lukewarm execution scenario, okay? So then, let's see, how are we doing on time here? Okay, I'm gonna wrap up in a couple of minutes. So kind of the key observation here, key insight is that there's very high commonality across invocations, right? So every time the same function is invoked, we see very high commonality in the instruction cache blocks across executions. This observation is highly related to the previous part of the talk, right? So in that part of the talk was looking at which pages are common, and this one is looking at the individual cache blocks. Pages are made up of cache blocks, right? And so it's not surprising that there's extremely high commonality at the level of individual cache blocks. And then we find that there's a very large instruction footprint of hundreds of kilobytes. Again, so this is in a way surprising, almost a megabyte of instruction of code for a function that runs in like literally a couple of milliseconds, right? That's pretty shocking. And that has to do with really, really deep software stacks that are like user code, kernel code, network stack, communication fabric like gRPC, runtime, right? Like basically we're just streaming through code when we execute these things, okay? And so basically, kind of this work identifies a common problem for serverless functions, which is there's a large instruction footprint that simply cannot be maintained on chip under heavy interleaving. And so the idea is really straightforward. We're basically at the end of the talk now, right? It's conceptually, it's exactly the same as before, but now in the microarchitecture, right? It's to record, exploit this commonality across invocations, record the instruction working set at the cache line granularity now, not pages, but cache lines, record it for one invocation, save it somewhere in memory, right? And then when the function is reinvoked later, right, we're going to restore the cache blocks associated with the instructions, bring them back on chip proactively using a hardware prefetching mechanism, okay? And so we kind of have this scheme called jukebox. Again, this is not a microarchitecture talk. I'm not going to drag you through the, kind of the bits and the wires of the system, right? But the idea, as I said, is to basically record all of the cache misses for instructions when the function starts running, right? We do this in hardware. And then a dedicated hardware unit will basically restore these when the function is reinvoked again, okay? Key performance result, kind of compared to the baseline system, Jukebox improves performance by 18% on average. It needs only 32 kilobytes of in-memory metadata in order to do this recording, right? So 32 kilobytes, this is stored in main memory. I mean, compared to a function that takes, tens or hundreds of megabytes of memory, I mean, this is nothing. This is like well under 1%. I mean, this is like 0.1, 0.01% of total function memory footprint. Okay, so it's simple and effective. So to recap, right, kind of recapping the entire talk, serverless functions are, kind of hot trend, really interesting, very, very different way to deploy and run software in the cloud than, virtual machines. lots of challenges, lots of opportunities, right? I talked about the vHive kind of ecosystem that enables research in the serverless world, right? I talked about a couple of projects. The second one was this kind of jukebox that is basically identifying a particular bottleneck due to the fact that all of these functions are interleaving on a server, right? And I showed that how very, very simple hardware, and you have to take my word for it because I didn't spend enough time explaining it, right, can improve performance of warm serverless functions by about 18% or so. Okay, lots of people have worked on this. Actually, this list is incomplete. We've had more people help since then. And yeah, with that, I'll conclude, and I'm super happy to take questions.
Thank you, Dr. Boris. I see we have questions in the Q&A. For that, I had in part one, I was wondering what were some of the design considerations that went in choosing Firecracker micro VM over something like a Docker container?
Okay, great question. So, so this is actually a really good question because, you know, in a way, it's a two-part question. So the first part is Docker and micro VMs. So it's not one over the other; it's actually both. So containers. So we use both, and that's again what every cloud provider, almost every cloud provider, does today. So people use containers because it just really, really simple to deploy software, right? You package it up as a container, you upload it to the cloud, and so then, like, you know, you have Docker containers. Everybody would love to just run in containers. The problem is containerization does not provide enough security. And so for security reasons, people run VMs. Nobody wants to run VMs. They run it because they want that additional layer of security. So it's containerizations for deployment simplicity, right? And it's VMs for security, but ultimately containers run in VMs. So it's both. And the reason why we use what was the Amazon one? A Firecracker is because we mostly focused on this like AWS-like stack. Again, I want to be very careful. Obviously, it's not AWS, but it's the stack that we knew the most about when we were building the system. And so we predominantly focused on that. So you're muted, I think, or at least I can't hear you.
Thank you. Dave Loper asks, are algorithms like LRU or MGLRU to be used to keep some functions online longer in case they need to be called again?
Yeah, awesome question. Awesome question. So in a way, yes. So basically what cloud providers do, I mean, you're completely right. You know, like obviously you want to kind of maximize the utility of a deployed function, right? Because it does take time to bring it back up. That is in the critical path. It takes resources, right? So cloud providers are not stupid. And so what they do is they basically, a function that has been invoked, they will keep it around for some time. The exact time interval depends from provider to provider, but we find, because we've actually experimented with like a bunch of different real providers, and what we find is that something on the order of around 10 minutes, you know, give or take several minutes, and it varies across providers, seems to be like a typical number. So every time a function gets invoked, that kind of timeout thing gets refreshed. And if it hasn't been invoked in, you know, this ballpark 10-minute time frame, then they'll shut down that particular function instance.
Thank you. Our next question is three parts. One, could you please elaborate on the change in code that would happen typically when transitioning from microservice architecture to serverless? Two, why was gRPC chosen as the protocol? And three, why is it not profitable for a cloud service provider when an instance is sitting idle, even though it is being paid for?
Okay, cool. So let's go through these in order. So serverless, so change, you know, what are the changes in code that are necessary to port from microservices to serverless? So serverless functions have to be stateless, right? Like that is fundamental to serverless, right? Microservices don't have to be stateless, but if you actually have worked with microservices and if you follow microservice best practices, it is recommended to make them stateless because that makes them more agile and also more resilient. So like if a instance goes down, you don't actually lose valuable state. So if your microservice-based application actually follows these best practices and it is stateless in that case, right? Then it's pretty darn simple, right? Like you basically have to kind of we're really talking about wrappers on the code. This is the best case scenario. Now, if you have microservices that are stateful, then you either have to peel apart the state, right? So you kind of have to break them up into stateful and stateless components, or you keep those things as microservices and you deploy the rest as serverless. So there's potentially a little bit of a design decision, right? That really depends on the application. But generally speaking, again, our experience is that it's not really a lot of work. Why was gRPC chosen as a protocol? There are basically two most popular open source options, gRPC and Thrift. To be extremely honest with you, I don't know why exactly we went with gRPC. I think maybe it had to do with like just being a teeny bit more familiar with it. I don't think there's like a really fundamental reason. And then the last one, why is it not profitable for a cloud service provider when an instance is sitting idle, even though it is being paid for? So it's not that it's not profitable. Like a VM is being paid for, they're making money on it. But the question is that CPU is idle and that memory is utilized, right? So like, if you're a provider, you think, well, okay, I'm making this much money on this idle instance that's consuming all of this memory. Can I possibly make more money by reselling that CPU and memory to something else? And serverless effectively gives cloud providers that option. They're basically saying, look, if you have VMs that sit around idle for a long time, maybe you should instead deploy your application as serverless, and then you only pay when it's being used, right? And then they basically take that, and then if people do that, right, then they take that idle CPU time and like, kind of physical memory, and they resell it at very fine granularity. And when you add up everything that they're billing for that, they actually make more money, right? So it's just a different way to monetize resources, but serverless is insanely profitable for the cloud provider.
Okay, I think you pretty much answered the next question.
Okay, cool.
Dr. Otu's asking, what do you think about the potential role for AI in enhancing security for serverless applications? Would it be effective?
Yeah, okay. So yeah, I mean, AI, I think that there is a cross section of ML, machine learning, and serverless. A lot of people are trying to deploy ML stuff on serverless. I think AI and security of serverless, wow. Yeah, I don't know what to say. I don't know what to say. I mean, the stateless nature of serverless in a way dramatically reduces the attack surface. Man, yeah, you got me there. Sorry, I don't know what to say.
Okay, thank you for your presentation. You'll be receiving a plaque and certificate from the Center for Cybersecurity Research. I'm sure we'll be in touch.
Awesome. Thank you so much again for having me. Really appreciate it.
Pleasure having you. Thank you.
Thanks for the great questions, everybody.
Have a good one.